Hi, I'm Mark Barsamian. In this video, I'll be discussing examples where we start with a function given by a formula, and we determine the intervals of concavity, that is, the intervals where it's concave up and concave down, and we find the inflection points. This material is in section 4.2 of the book, Second Derivatives and Graphs, and it's similar to stuff covered in the book examples 1, 2, and 3. The corresponding homework is this collection of 5 exercises from section 4.2. In those exercises, you're given a formula for f of x, and you have to determine concavity and find inflection points, and sometimes other things as well. So we'll just dive right into examples. Example 1, we will revisit a function that was used for example 2 in both the video for Homework 54 and the video for Homework 56. In those videos, we looked for intervals of increasing and decreasing, and we looked for local extrema. Those examples were similar to these exercises from section 4.1. In today's video, we will be doing things that are similar to what you're asked to do in these 2 exercises from section 4.2. So we'll start with kind of a review of things that were already done in section 4.1. Question A is, find the local extrema of f of x. Well, remember the strategy is find f prime, make a sign chart for f prime, and use the sign chart for f prime to answer the question. So there's our strategy. Again, we find f prime, we make a sign chart for f prime. That sign chart that tells us where f prime is positive and negative and 0 can be used to determine where f is increasing, decreasing, and horizontal. And it can be used, that sign chart for f prime, we will use to find the x-coordinates of the extrema in the graph of f of x. Now that will find the x-coordinates of those extrema. We'll go back and use the formula for f of x to find the y-coordinates of the extrema. So we found f prime, we factored it, and we can see that the partition numbers for f prime will be x equals 0 and x equals 3. So we'll make a sign chart. We've done all this before, so I'm going kind of quickly. So there's our sign chart for f prime. So we've done the first 2 things on our strategy. Now we have to use the sign chart for f prime to find the x-coordinates of the extrema in the graph of f. So we see that f prime of x changes from positive to 0 to negative at x equals 3. So that tells us that f of x will have a local max there. Okay, so we've done the third thing on our agenda. We used the sign chart for f prime to find the x-coordinates of the extrema in the graph of f of x. But now we need to find the extrema, that is, we need to find the xy coordinates of those points. So we have to do this. We have to go back and use the original formula for f of x to find the y coordinates of those extrema. So our local max has xy coordinates 3, 27. Now remember how the book presents this. The book often has you present sentences of this form. So that sentence makes it clear that the value of the local max is this number here, that's the y value. F parentheses 3 stands for the y value. That's the value of the local max. This symbol does a sneaky thing. It tells you the x coordinate where that max occurs. So that number 3 is the x coordinate. So that is the conclusion of our strategy. We did all 4 of those things. Question B, C, and D are about concavity. Find the intervals on which the graph of f is concave up or concave down, and find the x coordinates of all inflection points. Well, our strategy should be just like the strategy we used for question A. Our strategy for question A was to determine the sign behavior of f prime and use that to answer the questions. Well, we'll do this a similar thing using the sign behavior of f double prime. So there's our strategy. So let's go back up and remember what our f prime was. F prime of x was that function, minus 4x cubed plus 12x squared. So our f double prime is minus 12x squared plus 24x. We can factor that as minus 12x times x minus 2. So we will find the partition numbers for f double prime. We'll set f double prime equal to 0 and solve for x. We see that the solutions will be x equals 0 and x equals 2. So we've done the first part of our strategy. We found f double prime. And we have started doing some of the work for this sign chart for f double prime. We'll do that on the next page. So notice the first thing that I do is I label my sign chart. I give the name of the function and also its formula. So there's our sign chart for f double prime. So we've made the sign chart. Now we need to use that sign chart to answer these questions. The intervals where f is concave up, concave down, and the x coordinates of all inflection points. So f of x is concave up on the interval 0, 2 because f double prime is positive. Notice again the way that I explain this. I use nouns. I say, what is it that's concave up? It's f of x that's concave up. And what is it that's positive? It's f double prime that's positive. Also notice that I use the word interval because this symbol could be ambiguous. Somebody reading this might think that that refers to a point on the graph. It doesn't. It refers to an interval. So I said that it's an interval. So we have the intervals where f is concave down, 2 intervals. Now we need to figure out the inflection points. Notice that there are 2 places on the sign chart where the sign of f double prime changes, x equals 0 and x equals 2. So one of the requirements for an inflection point is that it has to be an x value where the concavity changes. So we've clearly got those 2 locations. But also an inflection point has to be a point on the graph. So we need to say very clearly why we know these are the inflection points. Those x coordinates are the locations of the inflection points because the concavity changes there and because we know the y value on the graph of f exists. We know that because f of x is polynomial, so its y values always exist. All right, let's go on. Question E is to find all inflection points. Well, wait, didn't we just do that? No, we found the x coordinates of the inflection points. Question D was to find the x coordinates of the inflection points. So we did that. In question E, we have to find the inflection points. That means the xy coordinates. So for that, we need to go back and use the original formula for f of x. Remember that. So we find the y-coordinates of the two inflection points. The inflection point at x equals 0 has a y-coordinate of 0. The inflection point at x equals 2 has a y-coordinate of 16. So we can give the inflection points as xy pairs. Let's go on. Question F says to illustrate all of our results on the given graph. Well, remember in the first part of the problem we found that there was a local max at 3, 27. So I illustrate that local max by putting a horizontal tangent line. Now in question E we found 2 inflection points. Now I often illustrate inflection points by putting a little X on the graph. So those are the 3 important points. Notice there is a horizontal tangent line at x equals 0, but there's not a max or a min. It's just an inflection point. Okay, let's go on. Example 2 is similar to 4.2 number 37. F of x is this complicated function. So we have to find the local extrema of f of x. So the strategy is find f prime, make a sign chart for f prime, and use the sign chart to find the x-coordinates of the local extrema, and then use the formula for f of x to find the y-coordinates of the local extrema. Hey, let's just copy that whole strategy from up above. There's our strategy. I'm going to copy that whole strategy and put it down below, and then we'll go back down and we'll find it there. All right, so there's the strategy copied from up above. So let's find f prime of x. Okay, so there's our derivative. Notice I recognize the form. The form is a nested function, so its derivative is found using the chain rule. And I did the chain rule details over here in this box. I used the empty version of the outer function. Remember that if a function is ln of x, its derivative would be 1 over x. But we have the function that's ln of parentheses, so its derivative is 1 over parentheses. Now, so we've found f prime of x. Now we need to make a sign chart for f prime. So for that, we need the partition numbers for f prime. We'll do that on the next page. So to find the partition numbers, we need to find the x-coordinates that cause f prime to be undefined or to be 0. So our first question is, are there any x-coordinates that cause f prime to not exist? Okay, so we looked at the denominator to see if there were any x values that cause the denominator to be 0, because that would be the only way that f prime would not exist. And the key is that this equation has no solutions. Why? Well, you can try to factor that. You won't be able to factor it. Or you can use the quadratic formula. You'll find out that there are no solutions to that equation. So there are no x values that will cause f prime to not exist. So the only partition numbers for f prime will be the numbers that cause the numerator to be 0. So we see that the only partition number for f prime is x equals -3. All right, so now we need to make a sign chart for f prime of x. We'll do that on the next page. So there's our sign chart for f prime of x. Now remember, we're supposed to find the local extrema, so we'll use the first derivative test. Remember, the first derivative test is this. We have to find the places on the graph where the sign of f prime changes from negative to positive or positive to negative, and where the y value on the graph of f exists. Well, we see that at x equals negative 3, f prime changes from negative to positive, so that means that f changes from decreasing to increasing. And we know that the y value on the graph of f of x exists because f prime is 0. That means that there is a tangent line and it's horizontal. You can't have a tangent line unless there's a point on the graph. So we know that f prime changes from negative to 0 to positive, and so f must exist at x equals negative 3. And so that tells us that there's a local min at x equals negative 3. So we'll find the y-coordinate of the local min on the next page. So we have to use the original formula for f of x to find the y-coordinate of the local min. So we see that the local min is at the point xy equals negative 3 comma ln of 4. That is, the local min is the y value. All right, so that was our very long solution to question A, find the local extrema. Now question B is to find the intervals on which the graph of f is concave up or concave down, and find the x-coordinates of all the inflection points. So our strategy here is to study to find f double prime, study the sign of f double prime, and reach these conclusions. Well, f prime was this function, 2x plus 6 over x squared plus 6x plus 13. So f double prime will be the derivative of that. So there's our second derivative. It took us quite a while. Notice that it's very interesting. To find f prime, we had to use the chain rule. We had to find the derivative of f of x using the chain rule. But to find f double prime, we had to use the quotient rule. All right, now we need to make a sign chart for f double prime, so we need to find its partition numbers. So there are no x values that cause f double prime to not exist because the denominator is never 0. So the only partition numbers for f double prime will be the x values that will cause the numerator to be 0. Those will cause f double prime to be 0. So the partition numbers for f double prime are x equals negative 1 and x equals negative 5. So let's make a sign chart for f double prime. Notice that we know the denominator is never going to be 0. The denominator is squared, so the denominator is always going to be positive. So we can compute the sign f double prime parentheses negative 6 is going to be negative. We can compute that even though this is a horribly messy expression. So notice that we make our signs, and we in each case we know that the denominator is positive, and so the sign calculations are actually not as bad as it looks. And so there's our sign chart for f double prime. Now remember what we're doing here. Our strategy was find f double prime, make a sign chart for f double prime, and then use the sign chart to answer these questions. The intervals on which f is concave up, concave down, and the x-coordinates of inflection points. So there's our sign chart. We'll make our conclusions on the next page. So the first thing we do is we note the intervals of concavity. The places where f double prime is negative are going to be the places where f is concave down. That's 2 intervals. And the interval where f double prime is positive is the interval where f is concave up. And then these x values where f double prime changes sign are the x-coordinates of the inflection points. So f has inflection points at those 2 x values because f double prime changes sign and because f of x exists. Remember, we have to know that there's a y value on the graph of f of x. Well, the reason we know that f of x exists at those points is because f double prime exists. The only way that f double prime exists is if f of x exists. Let's go on. Find all inflection points. Well, that means we need to find the x, y coordinates. So our conclusion is that the y values are ln of 8. Let's go on. Question F, we're supposed to illustrate all of our results on the given graph of f of x. Well, what are our results? Let's go back and look at question A. Question A, we found that there was a local min at negative 3, ln of 4. ln of 4 is around 1.4. So there's our local min. Now in the most recent part of the problem, we found these 2 inflection points at negative 5, ln of 8 and negative 1, ln of 8. I'll illustrate those by putting an x on the graph. And I'll note the concavity. Notice that the graph is concave down out here very mildly, but the graph is clearly more concave up there in the middle, and then switches back to being concave down. And these y values, ln of 8, that's about 2.4. I'm sorry, about 2.1. That's the end of the example, and that's the end of the video. Thank you.